Question 3. This question is about transition elements. Okay, A part 1. Define complex. A molecule or ion formed by central metal atom or ion surrounded by one or more ligand. Okay, for example, in this complex ion, the iron 2 is a central metal ion and is surrounded by 6 ligand, ammonia. So together they are complex ion. Part 2. Table 3 gives some details, different complexes of the iron 2 and iron 3. So we have the complex EFG. Okay, so let's start from the first row. Okay, iron 2 ion. So ligand is ammonia. So coordination is 6. Means the iron 2 surrounded by 6 ammonia ligand, like what I told you just now, is octahedral complex. So the formula and the charge of the complex. So first is this iron with 6 ammonia, because coordination number 6. Ammonia is a monodentate ligand and the coordination number 6. So it's very clear telling us this is octahedral. Okay, something like this. And of course the charge is important because these ammonia, they are all neutral. Then the charge of the complex ion, it must from this iron 2. Okay, so now is a complex F. So this one is a okay, let's move to this part. The FeCl42 negative. So means this one is chloride as a ligand. So 4 chloride and overall charge is 2 negative. So it's telling us the iron now is iron 2 because positive 2, negative 4, overall is 2 negative charge here. So now we are quite clear, the ion is iron 2, ligand must be chloride, coordination number only 4, because 4 the diff bond. Something like this. Okay, this is a tetrahedral complex formed between the iron 2 and this chloride. Okay, the last one, last complex ion. So it's given this iron with 3 En. So this is a bidentate ligand. The coordination number also 6 because this one bidentate is 2 times 3, total 6 coordination number. So coordination number 6 here, and the ion must be iron 3. So why? Because the En is neutral, and the charge of the complex ion it must from this iron 3. So from here we can get all the answers, okay, and put into table. Part 3 completes figure 3.1 shows a splitting of the d orbitals in tetrahedral complex. Tetrahedral complex is it has 2 sets. The sets that with 3 orbitals, it will be higher in energy, and the set with 2 orbitals, it will lower in energy. So the higher 3 orbitals, higher energies 3 orbitals, they are d, x, y, x, z, y, z. And this lower energy level orbital set is dz squared, d, x squared, y squared. Okay, part B. Table 3.2 gives some details about this iron 3. So it's about care step. The hexa aqua iron 3. So the care step is 1. And in this second complex, so the care step is 1.4 times 10 power 2. And the last complex ion with 5 water ligand and 1 fluorine. So the care step is largest, 2.40 times 10 power 5. Okay, so now from these comparisons, we know that the last complex ion is the most stable one. because the K step is largest. There's a hint given from the info. And explain the reason for the difference in color of the two complexes. So we have this the first complex in the table and the second complex in the table. Okay, so the different color is because of the difference delta E, because there is a splitting. Remember this one, they are all octahedral. Octahedral means 2 orbitals higher energy level, 3 orbitals lower. And let's say this is the delta E for the first complex ion. And this is the delta E for the second complex ion, let's say. So because their energy level different, so between the d orbitals, so when the visible light pass through the sample, so the electrons in these lower energies orbital will absorb the light and get promoted or get excited. So same thing happened to this complex ion, another one. So the electrons in the lower orbital, lower energies orbital, it will absorb the light and undergo excitation. So which means the delta E now is different, and the electrons, it will absorb different wavelength. When the different wavelength being absorbed, then we will see different color. So that's the main idea. The main idea is always start from the difference d energy gap, the delta E, because different delta E electrons, okay, in this orbital, it will absorb different wavelength and it will get promoted. So when different wavelength being absorbed, then of course we will see different color. We will see different complementary color. Okay, part 2. Write an expression for the K step in the second complex ion. It always starts from the hexa-aqua ion 3. Okay, so how we know it's ion 3? Because this is the thiocyanate ion. This is negative charge. And overall is 2 positive. So we know that the ion is actually 3 positive. Right? So it's from the this hexa-aqua ion 3 ions with this thiocyanate or thiocyanate. So these, then they will form the new complex, and it will substitute 1 water ligands in this hexa-aqua ion 3. So this one is the equation. So we can use this one to form the K step. Okay, so concentration of the product over the concentration of the reactants. Do not put the water into the K step, so water excluded. So you just put the products over the reactants. Okay, so you get this one. Remember, put the square bracket outside everything to show that this is a concentration. Okay, like what I did here. Okay, part 3. Use information in the table 3.2 to calculate the value of the equilibrium constant Kc for the following reaction. This one you have to first construct this Kc expression. The concentration of the products, these two, over the concentration of the reactant, these two. So you get this Kc expression. Then if you look carefully, so you can actually use the K step value in the table. Okay, so this one is the K step 2, and this one is from the K step 3. So you can get from this table, you can check it out. So means basically is the K step 3 over the K step 2, because this part is 1 over K step 2. So means you just need to use the K step value, the last one over the second one. So you should get 1714. You can try it out. Try to construct another equation if you want. Great. This one is for the last one. Right. Last equation, and you can form the care step for the last complex ion. Right. Then you compare this care step 3 and the care step 2. You should get this answer, right? So it's a care step 3 over the care step 2. You should get this answer. Okay, part 4. A few drops of the Kf added to the solution of the hexa aqua ion 3, followed by a few drops of this potassium thiocyanate. Use the information in table 3.2. Describe any observations of each addition. Okay, first, when the Kf added, so what happened? The fluoride is added, means is most likely form the most stable complex ion here, because it's a fluorine. Means the fluoride will form this complex ion, highly stable. Then next step is look at the color, colorless. So means it's going to form the violet to colorless, because it's from this complex ion to this the new complex ion. Right. So the first observation is the solution turns from purple to colorless. Okay. Then the second addition is this potassium thiocyanate. So this one, if it's formed, then it will form the second complex ion. The second complex ion care step is lower, less stable. Means when we add the potassium thiocyanate, it will not really change the color, because this complex ion is more stable than the second one. So the solutions will not change color now. It remains colorless after addition of this KSCN, right, potassium thiocyanate. And okay, it's just because this complex ion is more stable than the second one. Right. From the care step value we know, once this complex ion form, it's quite hard to form back or to form this second complex ion, because this one is less stable. It will form less compared to the last one. Okay, part C. Hydrated compound J. So this is a compound, contains 3 green complex ion. So this one, this is a complex ions inside the compound J after it gets ionized. The value of X here, this one, can be determined by titrations of the sample of J with acidified this permanganate ion. And the acidified permanganate ion is one that oxidizes the oxalate ion. This is oxalate. And so this is the equation. This permanganate 7 ion, it will oxidize the oxalate ion, and this oxalate ion, it will form CO2 and H2O. And this permanganate 7 ion, it will form Mn2 positive. Right, so purple to colorless. So now you need to construct 2 half equation. Very easy. You just need to choose the correct pair. Oxidation of the oxalate, so you start from oxalate ion, and it will form CO2. So after that, you just balance it. Okay, again, you choose the oxalate ion, and it's from CO2. No need to put water first, no need. You just need to put the CO2 and balance it. So you just times 2, then the carbon and oxygens all balance. After the elements all balance, then you add electron, because here is 2 negative charge on left, here you put 2 electrons on right, so balance the charge. Okay, after that, the reductions of the permanganate 7 ion. So first you start from this one, and it's reduced to manganese 2 ion. After that, you try to balance the equation, balance the oxygen first. So on this left hand side, oxygens is 4, so you need to plus 4 H2O. So oxygens already balanced, then you need to balance hydrogen. So you need to put 8H plus on the left hand side to balance out this hydrogen. So last part is to balance the charge. So you just need to put 5 electrons, then both sides will be positive 2. Okay, part 2. A student prepare a solutions containing 0.1 gram of the J. The students titrate this solution with 0.02 mole per dm cube acidified KMnO4. The titer value is 12.2 cm. Okay, assume all the oxalate ions oxidized. Calculate the value of X here in this one, in the compound. Okay, give your answer to the nearest whole number, means the X. Okay, give the whole number. Now, first, you need to calculate, because the volume is given, concentration is given, so you can easily calculate the moles of KMnO4. So the moles of KMnO4 means the moles of this permanganate 7 ion. So you just use MV over 1000, you get the mole. So if the KMnO4 moles is this one, then the oxalate must be larger mole, because it's 2 to 5 ratio. So means to calculate the moles of oxalate ion, so you need to use 5 over 2 times the moles of KMnO4. Okay, because this one is larger mole than the permanganate ion. Okay, after that you get this one, 6.1 times 10 power negative 4. Okay, so once you get this, you need to know the moles of J. Okay, because this is oxalate. If you look at this formula, if this compound is dissolved, of course it will form this. Okay, it will form this complex ion. Okay, but in the compound J, you need to understand there are 3 oxalate ions there. So means these 3 oxalate ion, the C2O4, 2 negative, they will get oxidized. So the moles of J, then you need to divide by 3. So because from the salt we know that inside this salt it has the 3 moles of this oxalate ion. Okay, so after that you get 2.033 times 10 power negative 4. This is the moles of J already. Okay, so mole equal to the mass over molar mass. If you want to find the molar mass, so use mass over the mole. Okay, the mass 0.1 is given initially. This one, mass of J. So 0.1 over the moles of J, you should get 491.8. After that, you need to use this value minus this one, the anhydrous one. So the anhydrous salt already given, you use 491.8 minus the anhydrous, remaining they are all water. So over 18, you get 3 here. So the X number is 3. That's all. Thank you.